Hey, what's going on, guys? KIM-1 here. In this video I'd like to share my experience in emulating an interval timer for my KIM-1 emulator. So it might not be that trivial to understand what's going on actually and how it should work when you're reading through the documentation. Well, at least for me that was the case. So hopefully this video is going to be helpful to, at least to anyone who's trying to do sort of a similar thing. Alright, so let's kickstart with, let's kickstart with a hardware manual, because if I started here, probably would save me lots of time and effort, because the very first, here is the deal. Just want to give you the idea behind my confusion, guys, because otherwise it might not be that trivial to understand why I was so stuck with this. So yeah, probably even better to start here. So here we have the memory map for KIM-1 and know this location. So there are two timers because there are two 6530 routes in the original KIM-1. I'm emulating the timers only in the, I'm not sure the first one or whether the second, in one of them only. But anyway, so we have these essential addresses. So from 1704 to 1707, and when you have a look, the first confusion, just to give you an idea, so the first confusion, if you're dealing with a RAM memory location, so let's say like, I don't know, 0100, then you can actually write the data there and just write whatever data. That's clear, and that data like stands there, and that's not a big deal. However, if let's say you go to the location of 1704, for instance, need to go to the data. So 1704, and here we have what they call in the first book of KIM as, so another example, address 1704 connects to a very fast timer. Look at that address and you'll see time going by as a blur. And here we go, time going by as a blur. So here the timer is running at the clock speed, right? And if you just try to, so let's go to the data mode. So if you try to write there something, nothing really happens. It just doesn't change anything. If we go to the, say, location 1706, and again, like try to write there something, you see, like, strange thing happens. Well, actually, now it probably how it should work, because I'm writing, when I'm writing some data to the timer, it starts counting down. We'll counter this a bit later on. But anyway, it's not the trivial behavior. It's not the standard behavior that you're used to see in the KIM monitor. And for me personally, that was the very first point where I got extremely stuck. And if we go, say, for address 1707. Then here, no matter what we try to enter, it just goes to this hexadecimal 80, and you might be wondering why the heck is that going on. So this is the starting point, and just to give you, just to lit a fire a bit, I need to say that, well, currently I'm not sure whether this behavior is exactly what the exact behavior that should be on the real KIM, but I think it is like something sort of that. But anyway, so if we go back to this, I hope now it gets a bit more clear. So we now go back to this memory map. So one thing missing here, so another thing, so in the documentation, well, even though it's sort of a homebrew documentation still, here we have the missing part. So you see, like, for addresses 1706 and 1707, we have both what happens on the right if we write to that location, what happens if we read data from that location. But for 1704, we only have what happens if we write to that location, but nothing in regards to what happens if we read from that location. That's another issue. So sometimes this well, at least the homebrew documentation might not be that perfect, even though this one is something that I really like. But anyway, so the first confusion that I had is I was wondering, I was thinking that if we have up to like, so let's start with writing to memory addresses. So if, let's go to user manual. yeah, let's start from here basically. That's where I started. So the KIM-1 interval timer allows the user to specify a preset count of up to 256, and I believe this stands for decimal counting system, and a clock divide rate of 1, 8, 64, and 1024 by writing to a memory location. And yeah, okay, so as soon as the write occurs, counting at the specified rate begins. The timer counts down at the clock frequency divided by the divide rate. The current timer count may be read at any time. And this sort of a phrase, the current timer count may be read at any time, was made me think that there are up to 4 timers. So I was thinking that as far as we have the 4 addresses, there should be 4 timers. So one timer is going at this divide rate, another timer goes at this, another at this, and another at this. But and this has been fooling me for quite a bit of time. And I was when I tried to implement this, I had actually 4 timer variables, and that was a complete disaster. So it really didn't bring me anywhere until I found this hardware manual. And here in the hardware manual for KIM-1, I realized the following thing. The timer section of the MCS6530, which is the right chip I was talking about, contains 3 basic parts: preliminary divide down register, programmable 8-bit register, and interrupt logic. So we can omit the interrupt logic for now, just for simplicity. But these two are absolutely essential. So let's read further on. The interval timer can be programmed to count up to 256 time intervals. Each time interval can be either at 1T, 80, 60/40, and 10/20/40, which we're familiar with already. Increments, where the T is the system clock period. When a full count is reached, an interrupt flag is set to logic 1. After the interrupt flag, well, don't really care about the interrupts currently. But another important thing that if we go back to the user manual, here is another important note. So since the counter never stops, continued counting down will reach 0, 0 again, then FF, then count will continue. So I was confused by the fact that we have 2 sort of things. So the first thing, that counter is constantly counting down, but on the other hand, we can reference the current count of the timer, but only regarding to the fact when the certain value has been set to the timer, and when the timer has completed, like from that value, like from FF to down to 0, 0, and then we stop counting. And then even though we have stopped counting, the timer is still counting. So what's the difference between the timer that has stopped counting and the timer that still counts? So like, it's absolutely mind-blowing thing. However, what helped me to calm down a little bit and get with it, I'm not sure whether this is actually true or not, what I came up with eventually, but at the very least now I have a sort of working timer on my KIM-1, which still needs to be tuned, because the delays might not be accurate, most likely. But anyway, at least it works at some point. So let me give you an idea. So here, I'm real dumb in the hardware, but what I understand from this diagram, that the divide down register is something that physically counts from FF and then to FE, FD, FC, FB, FA, and downwards until it reaches 0. And then when it reaches 0, it wraps around, so again, like it's FF, FE, FD, and downwards, and so on. And I believe that the programmable register, well, if I got the documentation properly, then I believe that this programmable register is somehow mapped to these addresses. So we can, by setting the values to these addresses, we can. I'm not sure if this is the case, if this is the exact case of what happens on the hardware level, but it seems like that once we alter these values, then exactly this programmable register gets altered, and depending on what value it has, the counting speed is actually changing. Again, I might be horribly wrong with this. I'm not claiming anything, but I just want to give you an idea that this sort of a diagram helped me to realize that there is the only timer. And you know, like, for those of you who is like thinking from the hardware perspective, these thoughts might be like a total mess for you. Might be considered as a total mess for you. But again, like, I'm a programmer, and when I'm trying to emulate something, I don't always have the exact understanding of how the real hardware works, and that's bad, I know. But anyway, but when I saw this diagram, I realized there should be just one timer, and it just might behave in different ways. And this actually, because when you're trying to write a program, you really need to know at least how many variables you need to use for timers, right? So eventually, I'll show you the code, and we'll walk through the code as well. But just to get an idea, so we have a single timer here, and now let's drop back again to this section in the user manual for KIM-1. So I've been reading through this, I don't know, more than 100 of times probably. So let's go again, just trying to share my thoughts and also demonstrate how this works here. Okay, so the KIM-1 interval timer allows user to specify a preset count of up to 256 and a clock divide rate of 1, 8, 64, 10, 24 by writing to a memory location. So first, when we write to the memory locations to this one, this actually sets the timer divide rate. The fact of writing to these locations sets the timer divide rate. And the value that we're writing to these locations actually sets up the count from which we will start to count down until reaching 0. So that's essential. So two parameters. The fact of writing to address actually, well, at least from the programming perspective, I'm not sure if that's the case from the hardware perspective, but from the software perspective, once we write to the address, what we have this specify rate being set up, and in the code I do just different delays depending on which address we're writing to, right? So, and then the value sets the count. Okay, so let's read on. As soon as the write occurs, counting at the specified rate begins. So this is important. This is what I've just said. So once we're writing to, we have like STA 1706, for instance. So whatever we have in the 8 register, we're writing that value to the 1706, and the value that we've written is the initializer for a counter. So counter would start counting down at that value at the rate of the 64 multiplied by clock cycles speed. Let's drop this for now. Okay, so as soon as write occurs, counting down at specified rate, just counting at the specified rate begins. The timer counts down at the clock frequency divided by the divide rate. Yeah, that's more the better way to see this. The current timer count may be read at any time. That's another important thing. So the current timer count may be read at any time. But I was thinking when I was like, this current timer count may be read at any time, but it might be read at any time until the timer is running, but when the timer has stopped, it may no longer be read. And that's just my assumption. I might be horribly wrong here, but at least from the perspective of how the programs relying on the timers actually work, this should be the case. Okay. At the user option, the timer may be programmed to generate an interrupt. We don't care about interrupts currently. When the counter counts down past 0, when the count 0 is passed. Okay, so the divide rate is, well, another important thing. Yeah, when a count of 0 is passed, the divide rate is automatically set to 1, and the counter continues to count down at the clock rate starting a count of FF. And assuming the current implementation I have, I've just separated the logic of counting down the clock rate and counting down at the user specified rate. So these two are in my particular implementation, they are separated. And the reason for that, because I always want to have this so-called time blur, which in most programs is used as a source for random numbers. And if I did this all in one, like they state in the documentation, I would have need doing this asynchronously, and that would be slowing down the emulator, and the cycle accuracy would have been messed up in that case. So I decided to split this logic. So this happens synchronously, hence it doesn't affect doesn't impact the overall speed of the emulator. But once I'm running the timer, it actually does affect the speed. But in that case, as far as it's still going asynchronously, so probably the overall like megahertz like drop down a little bit, but from the user application perspective, that doesn't seem to be that horrible. All right, so let's go further on. So this allows the user to determine how many clock cycles have passed since the timer reached a count of 0. So don't care about this for now. Since the counter never stops, this is important. Since the counter never stops, continue counting down will reach 0, 0 again, then FF, and then the count will continue. So it kind of like never stops counting, and this is represented here the address 1704. And by the way, the only place where I found what we should see if we navigated the address 1704 is again like this first book of KIM that tells you that another example address 1704 connects to a very fast timer. Look at the address and you'll see the time going by as a blur. And also again like in the programs, when you want us to feed the random number from 0 to FF, they use this address as well. So like in the Farmer Brown game, for instance, so in order to like send different animals like ants or dogs or fox or elephant or bird, so in order to pick up next animal to send, it actually uses the 1704 address as the source of a random numbers. And if this is not set, for instance, in your either emulator or real hardware, it just won't be generating random numbers. It's always going to be 0, whatever value we have there. So just going to be and going all of the time instead of other animals. All right, so what else? And now further on. So loading the timer. The divide rate and interrupt option, well, we don't care about interrupt option for now, are programmed by decoding the least significant address bit. So here we have the least significant address bit, and by decoding this address bit, we actually specify the divide rate. So, and again, like if we take this addresses, then interrupt is not enabled, is disabled, and if we use this one, interrupt is enabled. But since at the moment I have no idea how to deal with those interrupts in the emulator, because I still can't wrap my mind around this. Like I don't understand this. But if we just focus at this addresses, then it's enough to say that we have disabled interrupts here. So we really don't care about the interrupts here at all. But we do. But based on this least significant address, we have the specific like the corresponding divide rate being enabled. The starting count for the timer is determined by the value written to that address, and this is one of the most essential things in understanding the entire timers, how they work. So if I write a value to say 1707, no matter what we see, if we read that value, that doesn't matter at all. It would just write to that value. What happens in response? It would start counting down from the value that we've written to that address down to 0 at the speed of at the divide rate of 1024. If we do the same, if we write the value to 1706, it starts counting down starting from that value and down to the 0 at the divide rate of 64. Here the same at the divide rate of 8, and here is the same at the divide rate of 1. So probably now it's time to demonstrate how that works. I will now slow down things, but yeah, but that's essential to understand the principle, because if only someone could show me that, yeah, in the emulator code. Yeah, I really don't like when I need to implement something on my own. I really prefer to grab someone else's code instead of digging them out. But unfortunately, I didn't find one, so I really needed to go for my own experiments. Okay, so just trying to find where is my timer. Yeah, here is my timer, and yeah, here is the countdown. So here, if I say console.log, and here I just want to specify the count. Okay, so not going through the code yet. So let's just update this one and go into, just want to open the developer tools, go into console. In here, for instance, yeah, we don't really care about the addresses. For now, we don't care about the addresses. So if I just say, so I have a timer here. So timer, timer.write. And let's say, so let's write the value of FF to the address 1707. So this is the slowest timer. And you just see the speed of how the values would be scrolling. So here we go. And down back to 0. And we stop there. Okay, so again, like, notice the speed. So this is how we go. The speed is not accurate now. And again, like, it takes ages to write data to the console. But anyway, so you've noticed the speed, right? And now we write to this address, 1706. It goes faster, right? It goes faster. And if we write this to the address of the 05, it goes even faster. Maybe it's not seen here. I'll show you this in the emulator. Yeah, and here it should be like almost instant. Okay, so here it's the fastest one. So the speed of counting down is different, and I just wanted to give you an idea of what happens. So these values are the values of the count variable, and we're counting down starting from 255, which is the decimal representation of FF that I've specified here, and counting down and writing, counting down and writing, and so on. So that's clear. And now, as soon as this is clear, we can now go to the following thing. So here, another interesting thing to consider. So determining the timer status. After timing has begun, reading the address location 1707 will provide the timer status. If the counter has passed the count of 0, bit 7 would be set to 1. Otherwise, bit 7 and all other bits in location 1707 will be 0. This allows the program to watch location 1707 and determine whether the timer has timed out or not. So, in simple words, if the timer is not working, the location 1707 should be outputting the value of the bit 7 is set. It's the hexadecimal 80 when we have the bit 7 being set, which is like 0, 1, 0, 0, this is 8, and 0, 0, 0, 0, another null here, so 8, null, so 80, hexadecimal 80. Now let's have a look at this. Let's go for the same experiment, but we now go to the 1707, and it gives us 80. And why this is happening? That's because the timer has stopped, and even though we didn't run the timer yet, I'm not sure, but in those emulators I've seen, they usually have this 800s hexadecimal set there by default. And now you just notice what happens. So I will now try to write to this address, and by the time it would be counting, the value here would be 0, which means that the status of the timer is busy. So 00 at 1707 means the timer is counting now. So you just have a look here and just hit enter and counting and done. And again, like, and countdown, 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 and done. And again, countdown, 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 and it's done. Now let's try to write to the address of 1706. Now it should be faster, all right? And now it's faster. You see, like, it's a little bit faster now. And now if we just try to write to 1705, now it should be even more faster. Okay, now it goes even more faster, right? And if we write finally to the address 1704, it's almost instant. Well, not really, but yeah, I still need to tune this timings. But anyway, you just have an idea that this status kind of works here. All right, so far so good. Let's go further on. Yeah, so reading the count in the timer, and this is another mind-blowing thing. But anyway, if the timer has not counted past 0, and this is so essential. If the timer has not counted past 0, which means that from the status perspective, we have a value of 0, 0 at the location 1707. So this means the timer is still running. This didn't yet pass the 0 count. Reading the location 1706 will provide the current timer count and disable the interrupt option. The same for 1708 will provide the current timer count and enable the interrupt option, but we don't care about this at the moment. If the timer has counted past 0, reading either memory location 1706 or 1708 will restore the divide radio to its previous program value. So this is a little bit unclear to me, but again, since I have the timer running at the clock speed and the one that starts like on user demand, it feels like I have two different timers. Actually, this is the one timer, but as far as I don't clearly understand how this works and don't really want to overload my emulator with this background jobs, I really just separated this thing. So I don't really care about this. Well, this for now. Maybe that's not good. Well, not sure. So disable the interrupt option and leave the timer with its current count. No, disable the option. Leave the timer with its current count, not the count originally written to the timer. Not really sure what this means, to be honest. So in my case, when it just counts down to 0, it just stops there at 0. So I still need to verify how exactly the 1706 address behaves on the real hardware, and yeah, that's going to be helpful. Because the timer never stops counting, this is another important thing. So because the timer never stops counting, I believe that's happening because of this preliminary divide down register, which I believe this guy is never stops counting. Might be wrong though. Because the timer never stops counting, the timer will continue to decrement past 0, set the divide rate to 1, and continue to count down at the clock frequency unless the new information is written to the timer. Something I don't understand here still is when the timer has completed its count, what should it do next? So should it be like blurring like at 1704? But the same as the 1706, or maybe not. No, that's a question. But anyway, just to demonstrate how this location of 1706 works, and we go for exactly the same experiment. So for instance, we go. So you just notice how it would start counting down now, and here we go. So this is the slowest one, right? Counting down. Again, here I'm not sure whether it should be 0 or maybe it still should be counting. Not clear about this. Still need to figure out. But anyway, if we try to make it slower, then faster. Okay, we were going faster, and now going even more faster, even faster, and going even faster. 1704. So this, in theory, should be at the speed of the clock. Not sure if this is, again, like if the timing is proper here. But anyways, I just want to say that this one is much faster than this one, which kind of sort of represents the behavior of what the timer's behavior should be. Okay, so I hope this is clear, at least to what I currently have. And just to give you an idea how this, now I want to show a couple of programs that actually do rely on this timer. And then at the end, we'll walk through the source code, or maybe, yeah, probably maybe which. Let's walk through the source code first. Yeah, let's walk through the source code of this emulated timer first, and then better we'll end up the video with demonstrating a couple of real-world programs that actually do rely on the timer. So here is the code. The timer in my case is, it's not really a class, but provides sort of an API. So I have the timer variable. In order to create timer, I'm doing this new timer. And here, well, if this was a class, then these guys could have been, you can think of these guys as the internal class fields, and these are the methods. Don't care about the private or public. Well, actually, these are private, and here is the public API. So this timer object has three public functions. So the tick, read, and write. And now this tick, you remember I've been mentioning that I've separated the logic of counting at the clock rate and counting down on user demand, just to make the performance better. So this tick is fired every time the CPU steps. So here's the main loop where the CPU steps. So the CPU steps, right, and the timer ticks. So in my world, in my head, this kind of means, so if we have a clock pin on the timer, and in order to like increment the value, or in our case to decrement the value within this divider, like, you got what I mean. Okay, so we have the clock pin, and once the clock cycle on the CPU fires, it like ban and one more and ban and one more, ban and one, I mean like one last. So this is how I synchronize the clock signal. Like, let's imagine that the CPU generates this clock signal, and timer ticks at the same time. And yeah, as far as this is not happening asynchronously, this is just quite pretty fast. And this timer tick, it's very like, it's not processing power, not the processing power consuming task. So all we do in the tick, we just decrement the timer, and here is the variable. And the only purpose of having this variable, actually, the only purpose of doing this is having this the location 1704, having this time blur. So here I'm printing the value of the timer is returned there to when we're reading to the address 1704. I'll show that later on. So a timer decrements, and if timer is equal to 0, it wraps around to FF, and that's how it's implemented. So from FF to 00, from FF to 00, from 00 to FF, back and forth all of the time. Okay, so now this is clear. Now read function. Yeah, don't need this anymore. And as well as this one. So what happens when we read? So there might be up to 4 addresses: 1704, 05, 06, and 07. So depending on which address we're looking at. So if we're so when the user navigates to the address 1704, I return the timer here to make what they want in this the first book of KIM. So we go to 1704 to see the very fast timer, time going by as a blur. So in order to make this sort of an effect, and that's the only reason why I use this timer variable. So once the user goes to 1704, I just return this timer, which is in the range between 0 and FF, and is used as the random number, as the source at the feed of the random numbers. I have no idea what should be happening on the 1705, so we just have a look at this reference. So 1704, no idea what's in the input, but I know that there should be this time blur. 1705, no idea if what should be there if you read from that address. But anyway, we know 1706 and 1707. So 1706 is the timer, shows the timer count, and 1707 shows the timer status. And I have this variable, so I have a count which is set by the user if he writes to that address. So here it would be seen, right? And the status is whether the timer is busy or not. So if user is asking what is available at the address 1706, it returns the current count. And if user is asking what is the address 1707, it returns the current status. Okay, so far so good. So now let's go to the write function. So here, count, the very first thing to consider, count takes the value that we becomes equal to the value that we're specifying there. So what I've been doing here, for instance, when I was writing to when I was doing this timer write, so I've specified the value to start counting down from. So here I want to start counting down from FF, for instance, and this FF, this value is equal to FF in this case, and we initialize this internal count to FF, and then the interesting part begins. So depending on the address, we're starting to count down with the different delays, and these delays are derived from the clock divide rate of 1, 8, 64, and 1024. They were available somewhere probably even in the first book of KIM. They are available as well, but I took them from the source code of KIM-1. But anyway, so we go into this countdown, and here is the countdown, and this is the most interesting. This is the most interesting function. So it decrements the count, right? And then it asynchronously, it calls itself asynchronously, but it's not a recursion. If I would have made it like this, it would be the recursion, but in this case, it's not a recursion. It's just calling itself asynchronously, and this sort of mimics how this should behave when you just. So this is the way to emulate this, what they call the divide rate. So instead of dividing something, I just specify the custom timeout, and next time the countdown function is called, and it's not called recursively. This is important. It's not recursive call. It's just asynchronous timed out call. That's what the set timeout does. So it's called after the certain delay. So for instance, if we're writing this to 1704, the delay would be this. If here, this is the delay, this is the delay, and this is the delay as well. So these delays are in milliseconds. All right. So we're doing this countdown with a delay, which allows us to mimic the speed. But once the count is less than 0, so for instance -1, right? So the status turns to 80 hexadecimal, which means that we're done counting, and the count starts being equal to 0. Well, I'm not sure whether the count should be 0 here or not, so it's not clear for me. But anyway, and then it returns. So yeah, and by the way, by the time it's running, the status is set to. So it's just to make it even more readable. Maybe this is the way to go. So by the time the counter is counting down at the user-defined rate, the status is 0x00, which is busy, which means busy, and yeah, it decrements the count. But once it's done, the status becomes 80 hexadecimal. The count's not sure this should be equals to 0, and the most essential we return from this function. So we're no longer doing this background calls like asynchronous calls. And again, this is time consuming, so this slows down the entire emulator, and this is not really that good, but that's how I managed to do this so far at the very least. So yeah, this is pretty much all about the timer, and just to show you where I call this timer read and timer write. So in the CPU read, so the function that reads when the processor reads the value from the memory, so we're going within the address range of is greater than 1700 hexadecimal, so we're in the writes territory, 76530 writes territory address range. Here we'll read the timer, so the address is in the range of 1704 and less than 1707. And so here is just the code dealing with the single step in mode, which I've taken from KIM-1, so nothing special here. So in the single step in mode, timer is always done, right? Yeah, and if we're dealing with this with the status and for rest, we just return what is there. But the major case is we actually just reading the timer. So you can ignore this part of code. So literally what happens if we are within this address range from 1704 to 1707, just read the timer. We just read, we call this timer read, and either getting the status at 1707 or the count at 1706 or the time going blur at 1704. All right, and when it comes to writing, when we have again like the 6530 write chips territory and the same address range, in this case we just simply write whatever address we have and we write the value. But no, we're not writing the value to that address. So value is just a way to trigger the user-defined delay to initialize that delay and start the counting down at that delay, and the value actually initializes the counters to start counting down from until it's done. And that's pretty much all about it. Okay, so this was theory, and now let's go for a bit of a practice. So the first program I want to show you is the one kindly provided by DOMINIC BUMBACA, who's created a sort of a program in 658 assembly to make use of timers. So by the time I was writing this, it said like the following code on CORSIUM is the modern KIM clone, will show a dash traveling across the screen one at a time, but shows a solid line on the emulator. So the reason for this was because it was just like no time in there and would just go in instantly. So that was the reason. Now let's just grab this code and I just copy this code and going back to the emulator and paste, assemble, upload, and go into 0200, and here we go. Here we go. And it prints one, and then another one, and then another one. I'm not sure about the timing. Still need to tune this. But anyway, you see like it now works at a certain speed, and now it's done. And now if we say, so here DOMINIC was setting the delay to 1707, which is the longest one. So let's try to make it a little bit faster. And I assemble the code and upload and go into 0200 and go. And now it goes a little bit faster, right? It really goes a little bit faster. Maybe not saying that clearly, but sorry, 0200 go. I break something already. Okay, sorry. Assemble, upload, 0200 go. So yeah, it goes a little bit faster. And now let's try. Now let's try this at 1705, which should be even faster now. So assemble, upload, 0200 and go. Yeah, now it goes even faster. And go. Yeah, by the way, I've added the feature to like click the buttons on the keypad using the keyboard, and I guess it should be here is the keyboard layout. So it's a new feature. It's not published yet, but by the time you would be watching this video, this version is gonna be available online. Okay, yeah, and the fastest one like this. So if I just stop first, assemble, and upload 0200 and go. And now it goes like the fastest possible way. 0200 goes the fastest possible way. So yeah, relies on the timer, and if just inspect the code a little bit. So, well, this part just prints the dash, so nothing special. Just prints the dash at the next in the next digit. But here is a delay, so every time, so every loop draws a next dash here, and before writing the next dash, it jumps to this delay subroutine. So the FF is the value for a timer to count down starting from, so from FF and down below to 0, and depending on which address do we write this to, it would be the countdown speed would be different. So here should be at the clock speed, it's much slower. So yeah, but anyway, and here is the most essential part. So we're checking the bit at 1707, so literally asking if it's 80 already, if it's hexadecimal 80. If it is hexadecimal 80, that branch plus. Okay, I'm just probably tired and might be talking some gibberish now, but anyway, so I just didn't. Sorry guys, I just didn't get into this. The idea is that depending on the timer status, so if the timer is counting down, we wait. If the timer is done, then we return from here. So that's the idea. Just too many things in my head, and my mind is blowing really, but yeah, so I just need to calm down a little bit and to work this out a bit better. But anyway, let's have a look at another example before I go. So another example is an application from the first book of KIM, and this is Timer by Joel SWANK. So timer turns KIM into a digital stopwatch showing up to 99 minutes and 59.99 seconds. It's designed to be accurate to 50 microseconds per second. The interval timer is used to count 9984 cycles, and the instruction between the timeout and the reset of the timer make up the other 16 cycles in 0.1 seconds. The keyboard is used to control the routine. Swollen, so 0 stop, 1 go for return to KIM, and 2 is reset. So let's give it a try. So here I just grab the paper tape and go into the timer, go into the converter, paste it here, convert into this what I call declare by dump, which is specific to this emulator, assemble and upload, and go into 0200 and go. And oh, come on. I should say 0 to start. Yeah. So once one is start counting. I'm not sure whether this should be 1 millisecond at the rate of 1 millisecond from the timer's perspective, or 1 second. It's completely unclear at the moment. But anyway, stop. Yeah. So I just want to show you the idea that we can run the timer and it kind of works. Yeah. And we can stop the timer and we can reset the timer, which makes sense. So yeah, the program that actually relies on this interval timer is working as a proof of concept. So again, like once I get done with tuning the delays, they should be quite accurate. But again, like for games, mostly doesn't really matter. This accuracy, this exact accuracy doesn't matter. So just some games just rely on timers, just to give a user some room to take an action on, like moving left to right or something, like an asteroids, for instance. I didn't yet test asteroids with these new timers. Yeah, I really need to do that, but I'm not going to be doing this now, because if it's not working, then all I said here it won't be worth much, really. Okay, guys, so I think that's it from my side. So I'm sorry for this, a bit of a non-technical approach to trying to explain how timers work, because I don't really understand that clearly enough on my own as well. Just wanted to share the approach that I take when I have no idea how to do things, and I just start tinkering around with these concepts, and eventually, like depending on what result we have at the very end, trying to figure out whether the approach was correct or not. So this is it from my side. Thanks for watching. Until the next time, and take care.